Hello and welcome back. In this video, we are discussing the principal unit normal vector. So sort of in your head, you should compare this to the unit tangent vector. So remember the tangent vector, or the derivative of the vector valued function. So just the tangent vector pointed in the direction of motion. So that was its direction. And then its magnitude was the speed. The unit tangent vector told us just the direction of motion, right? We stripped the speed away from it. We just found a unit vector in the direction of motion. So this kind of goes along with that. This is the principal unit normal vector. So what does this tell us? Well, this comes from that quantity we were looking at, that vector dt ds. Remember, we were looking at the direction, or rather, we were looking at the derivative of the unit tangent vector, how the unit tangent vector changed over time. So let me jump back to this image we should have of the unit tangent vector and dt ds, its derivative. Let me find that. Here we go. So maybe if I start here, that'll work. So here we'll use this gray vector as an approximation for dt ds for a delta s of 0.01. So pretty close to actually dt ds. And remember, we actually get dt ds by taking delta s to 0. But this will serve as a good approximation for our purposes. And remember, as we move along, this dt ds is telling us how the unit tangent vector is changing with respect to the parameter s. Right? So as we moved along it, there's a couple things we can notice here about it. One is it's telling us the direction that the unit tangent vector is changing. So notice here it's pointing inward along the curve because the direction of motion is changing inwardly. Right, as I increase s, it goes to the inside of the curve. Remember, its magnitude, the magnitude of this gray vector, is the curvature. So in previous videos, we just looked at the magnitude of this thing as it moved along. That was the curvature. But we also are going to want to get a hold of just the direction of this thing. Like what is the direction of this? Rather than just its magnitude, we want to think of it as a vector quantity. So thinking of this as a vector, we might notice something as I move along the curve, and that's that this dt ds is orthogonal to t, or at least it appears orthogonal to t. It looks like it's 90 degrees between those two vectors at all points. So I'd like to, in this video, prove that that's always going to happen, that dt ds is always orthogonal to t. And I'm actually not going to look just at dt ds. What we want here is just the direction of dt ds, and so that I'll get by dividing by the magnitude of it. So dividing by curvature, so scaling this by 1 over the curvature, gives me a unit vector in the direction of the turning. So I'll go ahead and turn on n here. This blue vector is n. So it's always going to have unit length. We're forcing it to have unit length by dividing by the curvature. And it's always going to point in the direction of the turning, so to the inside of the curve. All right, so this is going to be important for us to better understand acceleration of an object, and that's what this video is all about, is this principal unit normal vector. Why is it principal? What's the principal about, right? We understand the unit part of it is we're going to force this to have unit length. The principal part is there's sort of two choices for this thing, one pointing to the outside of the curve and one pointing to the inside of the curve. The one pointing to the inside of the curve, that's our principal one. That's sort of the one that we've chosen for all curves. That's our n. All right, so let me jump back to this. So how do we actually define the principal unit normal vector? Again, this is telling us the direction in which the object is turning, or direction in which the curve is turning. So here we have our smooth. We'll assume it's smooth, right? So remember, derivative, it's differentiable, and that its derivative is nowhere 0. And then if it's parameterized by arc length, in that case, right, we can find dt ds and divide by the magnitude of dt ds, which, remember, this is curvature. So the principal unit normal vector is 1 over curvature times dt ds. So notice this is a vector that's coming out. This is a vector quantity, and it's unit length. And that's the principal unit normal vector. That's how we get a hold of this thing that's telling us the direction of turning. Now, if we're not parameterized in terms of arc length, and most of the time we're not, we can use an alternative formula for this that'll also work, and that's dt dt. So we'll take a derivative of the unit tangent vector with respect to time and divide by the magnitude of dt dt. That'll also give us the principal unit normal vector in terms of the parameter t. And so in order to actually get a hold of this vector at a point along the curve, we need to find the parameter t that corresponds to that point on the curve, and then plug it in here, and that'll tell us our principal unit normal vector, giving us the direction in which the curve is turning. As I mentioned, this has some really nice properties. So two really important ones come to mind and are the subject of this theorem. The idea is that t and n are orthogonal to each other at all points of the curve. Right? So that means t dot n is 0 at all points. 0 scalar. The other thing is that the principal normal vector points to the inside of the curve. This one, we're not really going to prove this directly. That is really just coming from that interactive figure I just showed you. Kind of, at least motivates this fact. So I'm not going to prove this one, but at least it should be motivated that it should point to the inside of the curve, because again, it's a scalar multiple of dt ds. And we know dt ds is telling us the direction, the change of the unit tangent vector. So okay, so let's prove this one. So why is one true here? So we want to show that t and n, our principal unit normal vector, are orthogonal. So remember, we can do that by showing that. So that is t dot n is equal to the 0 scalar for all t. All right, well, why is this true? Really, this just comes from the fact that t is a unit vector, right? So recall that the magnitude of t at any point t is equal to, not equal to 0, that would be the 0 vector, is equal to 1. It's a unit vector. And if you remember back a few videos ago, we proved that if a position function, if a vector valued function has constant magnitude, then its derivative is orthogonal to it. So I actually want to go through that proof again in this context because it's a really nice proof to go through. So let's go ahead. I want to make sure I'm in the right. Okay, good. So why is this true? Well, right, magnitude of t is equal to 1. And so what that tells me then is, remember that the magnitude of a vector squared is the vector dot product with itself. So that is t dot t is equal to 1 squared, or just 1. This is a dot product. And notice that sometimes I suppress the input variable t. This t is no different than this t. Just sometimes I want to be explicit about the fact that this is a vector valued function, and other times it's implicit that it's a vector valued function, right? We should always be thinking of a unit tangent vector as not just one vector, but as a vector valued function that has different vectors when we put in different parameters. So this is t dot t is equal to 1. And this is neat because if I take a derivative with respect to t, time t, a parameter t, I should get 0 out. So then d dt of t dot t is equal to 0, right? Derivative of 1 with respect to time is 0. And then here we can use the dot product rule for derivatives. So this is derivative of the first. So I'll do dt dt, derivative of the first, dot the second, dot t, plus the first dot the derivative of the second. And we know that's equal to 0. We know dot products are commutative, so this is really 2 t dot dt dt. That's equal to 0. And hence t dot dt dt is equal to 0. So what that tells us then is t, the unit tangent vector, and its derivative with respect to our parameter t are orthogonal. And let's jump back to the definition of n again. Where's my definition of n? N is a scalar multiple of dt dt. So I'm thinking of this formulation here when our parameter is not necessarily an arc length parameter. So here it's a scalar multiple of dt dt. So that means n, so let's say, n is a scalar, well, let me just jump the gun there. It's a scalar multiple of dt dt, which means it's parallel to it. N is parallel to dt, capital T for unit tangent vector, dt dt. So if n is parallel to dt dt and dt dt is orthogonal to t, that means n is orthogonal to t. So n and t are orthogonal. And that's our proof. That's what we wanted to get out of this. And then remember the second point, that n is always pointing in the direction of the turning to the inside of the curve. So these are these two big points, and we've proved one and hopefully motivated the second one by looking at that figure. All right, so this over here gives us a way to calculate it in general. We can use this formula. So in the very next video, we'll work through an example where we find this principal unit normal vector for the helix. So before watching that video, you might think about what is this principal unit normal vector going to look like for the helix, keeping in mind these properties of the principal unit normal vector. I'll see you there.